In this video, I'm going to introduce the fundamental theorem of calculus and how it applies to anti-differentiation, or rather to indefinite integrals. So as the name suggests, it is fairly important in the study of calculus, so do make sure that you go through fairly slowly. Stop it if you need to, work through some of the examples before checking the answers, and just make sure that you're really comfortable with the content in this video before you sort of move on to the next thing. So we looked before at the idea of a definite integral being that it gives the area between the curve and the x-axis over a specified domain. So we had an example, maybe something like this, where you've got a curve, sort of like maybe a rectangular hyperbola, not sure. Well, yes we are, because it's got 1 over x there. And you'll find you want to find the area under the curve between 1 and 6. So we've got this definite integral, the integral between 1 and 6 of f of x, where f of x is 1 on x. And if you calculate that, then you will end up with that area under the curve there. Now, so far we've only considered functions where the value of the function is positive. So if we just go back here, so all these values are positive over that domain that we're interested in. So what happens when this is not the case? So if we have something like this, we have area under a curve, so where this is positive, but now we've got, it's still between the curve and the axis, but now it's actually over the curve, like under the curve, over the curve, under the curve. Okay, so do we treat those the same? Are they still an area, or is there something different? So let's go on and have a bit of an explore. So what we need to do is talk about the notion of signed areas, which means we have positive areas and negative areas, which when you sort of think from a practical point of view, it doesn't make a lot of sense, because how can you possibly have a negative area? But in terms of calculus, we do deal with areas that are above the x-axis are positive, and areas below the x-axis and negative. So in this case, this is going to be a positive area, and this will be a negative area. Okay, so it doesn't mean it actually doesn't exist, it just we signed it negative. So from a geometrical point of view, the area between the curve and the axis is the absolute sum of the two areas. So in this case, if we were saying, well, we want to know what's the area between the curve and the x-axis from -2 to 2, you work out this little triangle and you'd add it to this triangle. So you'd end up with A1 plus A2. However, if you're considering the signed area, then it will be the sum when you take the signs into account. So it'll be A1 plus A2, but A2 is negative. So we do A1, this triangle, subtract A2, and that would give you the signed area. So let's have a look. This is fairly straightforward, obviously, because we've got triangles, so easy to work out. Would be slightly more complicated if you had a quadratic or a cubic or something like that. Okay, so A1 is going to be a half of the base times height. Base is 3, height is 3, so we've got 4.5. A2, also half base times height, except the base is 1 and the height is 1, so that's 0.5. So the total area of A1 plus A2 is 5, but the signed area will be A1 minus A2, and that is 4. So now we sort of face the interesting problem where we have the same question but two distinctly different answers. So which one is the one that we actually need? So if we go to the definition of a definite integral, what we've got is for any continuous function x over an interval given, ab, the definite integral, which means when you integrate between the 2 points, the given interval, it will give the signed area enclosed by the graph. So we'll take into account the fact that negative areas, or areas below the x-axis, are negative. So in this case, the answer to this question, if you were to say, well, what is the integral, the definite integral between -2 and 2 of x plus 1, then you would get the answer 4, not 5. Okay, and you can do this on your class pad, just to show you. So we want to type in, we had x plus 1, okay, and then we are going to go calculation, using your integration, we're doing definite from -2 to 2, go, and it will give you 4. Okay, so that is the signed area, taking into account that areas below the x-axis are signed as negative. So now we come to the actual fundamental theorem of calculus, and basically it states this. If you have the definite integral between a and b of some function, then that area is equal to the value of the function at b minus the value of the function at a. So this is your derivative, and this is your function. Okay, so we'll do a little bit of exploring with our first example. So this is the example that we had, but now we're going to do it using the fundamental theorem. So we're saying that minus 2 to 2 of x plus 1 dx, okay, and we think that's going to be equal to the function. So this is if this is f prime of x, it's going to be equivalent to f, so the value of the function at minus, sorry, not minus 2, at 2, minus the value of the function at minus 2, from the top limit to the bottom limit. Now, we need to integrate this function in order to work out what it is, because we've got f prime x, and we want f of x. So, if f prime x is x plus 1, f of x is going to be x squared over 2 plus x plus c. Okay, so if we now do this, we've got f of 2 is 2 squared on 2 plus c. So that's how you get 4 plus c. Okay, we've also got f of minus 2 is minus 2 squared on 2 take 2 plus c, which will give you 0 plus c. And then when you do the subtraction, f of 2 minus f of minus 2, it gives you 4 plus c minus 0 plus c. And you can see that the c's cancel out, and you end up with 4, which is the answer that we got using our signed areas, and also the answer we got from our class pad. So in all cases, this c, this constant that we have here that we haven't been able to find because we haven't been given information about this curve, will cancel out when you are doing definite integrals, because there's one for the lower bound and there's one for the upper bound, and when you subtract them, it will cancel out. So we kind of just end up dropping that off. There is another way that we can write it, and that is to say that if we have from minus 2 to 2 of x plus 1, actually sorry, I'll do it in general terms, so f prime x dx, okay, that will be the value of the function from minus 2 to 2. So we write it like this, and what that just says is anti-differentiate this, work out what is the value of the function at 2, and then subtract the same value of the function at minus 2. Okay, so you'll see that in the examples that we do, we use this kind of notation just to make it a little clearer as what we're doing. Alright, so let's get straight into some examples. So the first one we've got there is integration between 2 and 3 of x squared. So say 2 and 3 x squared dot dx. Now that's going to be, I'm going to integrate this or anti-differentiate, so x cubed over 3, and between 2 and 3. Okay, so you put your antiderivative in here, and then you put your bounds. And what that means is evaluate for the upper bound, and then subtract the same, the value for the lower bound. So here we can go, it's 9 over 3, sorry, not 9, 27 over 3, subtract 8 over 3. Okay, and you end up with 9 take 8 on 3, or 19 on 3. Okay, so exact value for the area of the curve, the area under that curve between 2 and 3. Okay, for B, now B is really similar. The only difference is we've gone 3 to 2, so we're kind of going back the other way. And the effect that this has is just that it reverses the sign. Okay, because instead of doing 27 on 3 minus 8 on, minus 8 on 3, what you end up with is 8 on 3 minus 27 on 3. Because the antiderivative is the same, but now the upper bound is 2 and the lower bound is 3, so what you get is negative 19 over 3. And that's one of the rules of definite integration, is that if you reverse the upper and lower bounds, you just get negative of what you had previously. Alright, C, we've got between 0 and 1 of x to the power of a half plus x to the power of 3 on 2 dx. Okay, so the antiderivative there will be 2x to the 3 on 2 over 3 plus 2x to the 5 on 2 over 5, and we're going from 0 to 1. And you will learn to love it when we have either the upper and lower bound is 0, because it generally tends to cancel things out, which is pretty cool. So what we got there is 2 times 1 to the power of 3r2 over 3 plus 2 times 1 to the power of 5r2 over 5, and then you're subtracting, and basically subtracting 0, because that will be 0 and that will be 0. Okay, so I don't necessarily expect you to do this sort of business. I'm just sort of doing it so you can see where I'm substituting those values in, but you can skip these steps and just go straight to something like 2 over 3 plus 2 over 5. Okay, and that will give you 16 on 15. Okay, so that's a slightly more complicated one using some fractional indices, but exactly the same process. Okay, let's move on to the next example. So this one, again, same thing, evaluating each of the following definite integrals, but now we're dealing with some Euler's number in there. We do like these, we've got zeros in here, this is going to make life a bit easier. Okay, so from 0 to 1, 2 e to the negative 2x dx. So the integral of that is going to be negative 2 e to the 2x over 2. Okay, from 0 to 1. So that will give me negative e to the negative 2 minus negative 1, because of course these two cancel that out, and then anything to the power of 0 is 1, and we can just rewrite that slightly more neatly as 1 take e to the negative 2, or 1 take 1 on e squared. Okay, b, 0 to 4 of e to the power of 2x plus 1 dx. Okay, so integrating, differentiating this, e to 2x over 2 plus x, and going from 0 to 4. So if we start, I'm just going to move over here a little bit to give myself a bit more room. So that's going to be e to the power of 8 over 2 plus 4 minus, and that will just be a half, plus 0. Okay, so what you end up with there then is e to the power of 8 plus 7 on 2. Okay. And the last one, just doing some stuff with natural logs, or with reciprocal sort of functions. Alright, so we've got the first one here. Between 6 and 8, 1 over x minus 5 dx. And of course the integral there is natural log of x minus 5, and going between 6 and 8. So that would give you ln 3 minus ln 1, which of course comes out as just ln 3, because this is 0. And then for b, we've got between 4 and 5, 1 over 2x minus 5 dx. And of course with this one we need to make sure that we divide by the derivative of this function. So we did the same thing here, but the derivative here was just 1. So that's going to be a half ln 2x minus 5 between 4 and 5. So you end up with a half of natural log 5 minus a half natural log 3. We can take that half out. Gives me ln 5 minus ln 3. And of course then I can use my log laws to divide those, and I just get half natural log 5 over 3. Okay, and in most cases you would tend to leave it as an exact value, especially when you start dealing with logs. You don't want to be putting decimals in there unless the question specifically asks if it's some kind of modelling or applications question, and you need to have a number rather than natural log of 3, which doesn't make a lot of sense in practical terms. Right, so the main points that you need to remember from this video is that the definite integral gives the signed area, okay, not the absolute area as such, enclosed by a curve. The fundamental theorem is this little beastie here, okay, and we also write that as like this, between A and B, okay, and then there are some properties, and we'll deal with these a little bit more in the future, but if you make sure that those are familiar, most of them are fairly sort of intuitive, that will set you up well for more calculus.